good morning or afternoon or whenever you're watching this. I know it's probably a little dark in your viewer. It's the only way I can not have a huge amount of glare, so I apologize for that. But the purpose of this video is to go over what is a circuit and how does it work. So first of all, a circuit has to do with moving electricity. So we have here what I drew is two simple circuits, and a basic circuit consists of a battery, which is drawn as two lines that are parallel, one big, one tiny. Some wire, which is just a line, and a resistor. A resistor is drawn as a squiggle. Sometimes there's a circle around it. If you want to use a fancy resistor that lights up, that's called a light bulb. And you draw it as a little squiggle mark. So and that's pretty much the basics. So the moment you connect this, you allow a charge to move from the negative side to the positive. So remember what we are learning about charges. If you have a positive charge and a negative charge, they're going to attract each other. If you have two negative charges, they will repel each other, and that's how your circuit works. So you have a battery, and notice on all batteries, there's a positive side and negative side. And so all that negative side is where they clumped all of the electrons together, and the positive side is where they clumped all the protons together. And these negative electrons want to get away from each other so badly, so extremely badly. So if you give them a path, they can't just jump into thin air. It's really hard to do that. That's why lightning is so strong. But to do that, if you give them a pathway to get there, your little electron charges, so I'm going to draw that as a negative E for an electron, your little electrons will travel to the positive sides because they are attracted, and therefore escaping this extremely, extremely tight negative space where they don't want to be because they repel each other. And if you put a resistor in there, it stops them from going so fast they get excited and light things on fire. And so no matter what's happening, and if we put a light bulb there, we can make the electrons do things that we want to happen. Because as the electron travels, it carries with it energy. And before it can go back and hang out and chill with the protons, it needs to lose that energy. Because by the time it gets back to this side, it has no energy left. And so it gets that energy. All batteries have potential energy. It's stored in chemical form, but we can use that to make light, heat, and various other things move. That's how all of our tools use and harness the power in these electrons to make things happen. So let's, really quickly go over some definitions. So batteries, the purpose of the battery is that's the source of all of your energy. All of your potential energy is in that battery. Then we have voltage. You may have heard this term before. Voltage is just written with a capital V. And the voltage is how much energy there is per charge. So per unit of charge, there is some amount of energy associated with it. So like when we say have a 9-volt battery, such as the one I have here, if you have a 9-volt battery, that means each charge in there, each unit of charge in there has 9 volts. There's current, which current, just like a river current, has to do with the flow, how many charges per second. So you can kind of think of it like how many electrons are moving per second. The units for voltage is volts, so easy to remember. The units for current are amps, named after Ampere, who's the person who discovered them. And so between these two, these are your really big ideas. And the last one is resistance. We write that with a capital R. And resistance is kind of what it sounds like. It's just how much that material it's moving through resists that moving charge. And we measure that in ohms, which is either written as OHMS, ohms, or a omega sign. So let's kind of show this in action. So let's say I have a 9-volt battery because I have a 9-volt battery. And so I have a 9-volt battery. So each electron or each charge gets to carry 9 volts in it. But if I put an obstacle in the way, that electron has to expend its energy to get through it. And so after it goes through that single resistor on its pathway home, it has 0 volts. Same thing if I have another 9-volt battery, because I do. Each one has 9 volts again. They each spend their energy at this light bulb, and then they go home out of energy and go relax with the protons. And so in this way, this is how we have electrons do things for us. They have to be moving though. If you break a circuit, so if you've ever had a broken wire, it doesn't work anymore. If you don't plug it into the outlet, it doesn't work. If you don't connect the batteries, it doesn't work because you need to have a pathway for them to travel. If there's no road, the electrons aren't going to drive on it. So I'm going to erase this. And we're going to do a water analogy. So just like rivers and streams and waterfalls, let's use a waterfall. If you have a waterfall, this is a waterfall, by the way. All of that water in the waterfall starts with potential energy. If we increase the amount, or if we increase the height, if we add more height to our waterfall, that equals more energy. Height is going to be like your voltage. The higher it is, the more energy each one of those water molecules has because it's higher and higher, giving it more gravitational potential energy. The further it is from Earth, the more energy it has. So your height is kind of like your voltage. Also, if we increase the size of this waterfall, or you can think of it like this way, if I am increasing the height or changing the flow of my waterfall, so if I have more flow, I'm going to have more particles. Right? The faster my water is flowing, the more individual things I have actually moving through it. And so your flow is your current. Oops, let me do the squiggles. Is kind of like your current. So the more water that's flowing, the more energy is going through it also, right? Because a slow moving river is a lot less dangerous than a fast moving river. So the flow matters. Also, the height of it matters because also if it's starting higher, it's probably going to be moving faster lower, which is also true for circuits. If you have more voltage, you're probably going to have more current if there's nothing else going on here. The last piece of this is resistance, and we can add right here. There's really no resistance; it just gets to fall. But you could say add water turbines into this, or paddle wheels, or rocks. And so as you add rocks and terribly drawn paddle wheels, Imagine. Use your imagination, people. Ooh. As we add more rocks and paddle wheels and things in the way, that's our resistance. And so the more obstacles we have, it's going to slow it down. And so any obstacles to the path of our waterfall is like the resistance that we saw in the circuit. And so that's where we can get this basic relationship of V equals IR. Voltage equals current times resistance. And so what we're seeing is if we have more voltage, right, a higher waterfall, I'm probably going to get more current, right? Because the higher the waterfall is, the faster that waterfall is going to go, and that flow is similar to our current. So more voltage means more current. So that is, remember we talked about a directly proportional relationship. So the more voltage, we're going to get more current. The other relationship we want to talk about is the more obstacles I put in the path, the more resistance, the slower this is going to move, right? The more rocks and things I have getting in the way of the water, the slower it is. So the more resistance I have, the less current flow I have, or an inversely proportional relationship, right? If one goes up, the other goes down. And so current and resistance have an inversely proportional relationship, and voltage and current have a directly proportional relationship. If one goes up, the other goes up. If one goes down, the other goes down. And so this is the basics of, and this works for any ohmic resistor. We won't get into exactly what ohmic means. Basically, it just means it does follow this rule. There are non-ohmic things, but you do not need to worry about them. So again, quick review. Hopefully you learned that what is a circuit as far as a wire, battery, and something obstructing the path. How does it work as far as our voltage, current, and resistance? We have here our waterfall analogy, where the higher our waterfall is, that means it has more energy, and therefore more height means more voltage. Same thing, more flow, more particles, that's our current. And any obstacles in the way act as resistance, and they cause it to slow down. Quick thing on what if we don't have resistance, because I didn't talk about that. If you have no resistance, you have an out of control waterfall. AKA, if you have no resistance, you have an out of control circuit. Do not build circuits without resistances, because that's how you get fires. So you can do that in the PhET simulator and start a fire, but do not do that in real life. So I hope this was informative and you have a good rest of your day.